Today we're going to continue and, with a little luck, maybe even wrap up the discussion of plate tectonics, particularly with a final section focusing on how plate tectonics has affected our own local margin in California and actually the shape of California and the offshore as a whole. We may have to run over a little bit into Monday, but just to give you a little bit of a head start, actually we're going to start talking more about marine sediments and eventually about seawater itself come next week. So plate tectonics, this idea that the surface layers of the solid Earth, the lithosphere, which includes the crust and the uppermost part of the mantle, are broken up into a number of plates, 14, 15, depending on how you count the big ones, and some larger number of smaller ones, and that relative motions on the Earth's surface and a lot of the other interesting action actually takes place at the boundaries between these plates rather than inside the plates themselves, at which new oceanic crust and ultimately lithosphere is being created by volcanism as plates pull apart. New material rises up to replace it. The mantle that's rising up actually melts a little bit and makes new oceanic crust, new basalt. Okay, and so oceans are created at divergent plate boundaries, and they are recycled. The oceanic crust and the uppermost part of the mantle, the lithosphere, are recycled, pushed back down into the deep parts of the Earth at convergent boundaries. Okay? And in this case, we actually have volcanism as well, but the volcanism is not typically located right at the plate boundary like it is with the case of divergent boundaries, but is offset from the boundary somewhat, typically something like 150 kilometers, roughly 100 miles. And instead of being caused by upwelling of warm material from deeper in the Earth, which melts, these volcanoes are, we think, primarily a result of water released from the recycling oceanic lithosphere percolating up, because it's less dense than rock, percolating up into the overlying plate and causing it to melt by lowering its melting temperature. So it's melting not by adding heat, instead it's melting by chemically altering the material to lower its melting temperature, analogous to throwing salt on an icy sidewalk to lower the melting temperature of the ice. And there are different types of convergent boundaries depending on what parts of the plates are involved, what kind of crust is involved on either side of the boundary. And so we can have convergent boundaries where both the overriding plate and the subducting, the recycling plate, are oceanic crust. And as a result, you typically have, you have a deep sea trench everywhere, pretty much, where there's a convergent boundary. And in this case, you have volcanoes as well. But there's not a continent there. So the volcanoes tend to build up and make an arc, or a roughly curved linear pattern of volcanoes, some of which may break the surface and make islands. So that's a picture of the Marianas Islands in the western Pacific Ocean, where we have the Pacific plate going down and the overlying plate having volcanoes about 150 kilometers behind that boundary in an arc, and then another ocean basin right behind them. Or you can have oceanic crust, oceanic lithosphere going down in a convergent boundary underneath a continent. The classic example of this would be South America, which has a convergent plate boundary along its west coast. Hopefully you can all see this dark blue and purple band indicating the deep sea trench west of South America, where the Nazca plate, at least for most of this picture, the Nazca plate is going down underneath it. And then indicated in red here are active volcanoes, which again occur in a line roughly parallel to the plate boundary, but offset by 150 kilometers or something like that. And you can see that there aren't volcanoes everywhere, but they're fairly common parallel to that boundary. And of course, there are also lots of earthquakes, because there are earthquakes at every kind of plate boundary just about. So just a reminder, I've already mentioned this, but how that volcanism works. Okay, we have subducting lithosphere. The oceanic crust in particular has been cold. It's been sitting up under the ocean. While it was cold, it was sitting there. It was accumulating sediment. It was reacting with seawater. It was essentially becoming wet. And as it goes down, it starts to heat up. That water tends to come off, okay, and fluxes the overlying plate, reducing its melting temperature and typically causing melting, so you have volcanism. And then the final type of convergence is where you have a continent interacting with a continent across a convergent boundary. And the best example of this is India and Asia. Over the past 70 or 80 million years, India, which started out in the southern hemisphere, actually attached to southern Africa. We think when there was a supercontinent 200 and 250 million years ago, has moved northwards until something like 40 million years ago. It came into contact with southern Asia. Okay? There used to be an ocean in between those two continents. That ocean was presumably subducting, being recycled just like any other ocean-continent convergent boundary, but eventually you run out of ocean. The ocean's gone, the continent comes up against the continent. In that case, we have a continent-continent collision. Continents are simply too thick, not dense enough. They tend not to want to be recycled. They pop back up. Okay, like styrofoam on the surface of a pond, you can try to push it down. It's going to keep popping back up no matter what you do. It's not going to go down easily. Continents are much the same way with respect to the mantle. So instead of subducting, it crumples up at the surface, and you get a large region at high average elevations. In particular, in the case of India and Asia, India is pushing into Asia, and we're making this very large region, essentially Tibet, of high average elevations corresponding to very thick crust, because instead of being recycled, it's just piling up where the two are colliding with each other. And there are, in fact, ideas that this collision has been going on long enough and has thickened the crust so much it's becoming unstable, and stuff is kind of leaking out to the sides, so that Southeast Asia is actually kind of being extruded like toothpaste between these two anvils. Okay, so are there any questions about divergent boundaries, convergent boundaries? Yes?
As the India and Asia keep colliding, will that make Tibet bigger and bigger over years?
That's an excellent question. That's one idea for sure. That as India is pushing into Asia, Tibet is essentially growing broader and broader as a function of time. So if you go back 30 or 40 million years, Tibet might have been much narrower. And as it keeps pushing, it might get broader and broader. I don't know if it's fair to say that that's generally agreed to be happening, but that's one idea that's been floating around. The other idea is that there's this, what's called escape tectonics, that stuff is piling up here and is escaping. It's kind of slipping out, like a watermelon seed between your fingers, perhaps. Any other questions? Okay. So the third type of plate boundary, we've done divergent, we've done convergent. Third type is transform. Okay, and these are boundaries where you aren't making new crust by pulling things apart. You aren't recycling crust or colliding continents at a convergent boundary, but instead you have material, you have two plates that are sliding past each other more or less horizontally. No creation or destruction of material, just side-to-side motion. And the classic place to see this is in the ocean, where they're quite common, this type of boundary, interspersed actually along the divergent boundary. And so if we look at a close-up of the mid-Atlantic ridge, so here's just a little key map, here's South America, here's Africa. So if we just focus in on a little section of the mid-Atlantic ridge between Africa and South America, this is a bathymetric map. It looks something like this. You can see the ridge, this overall area of relatively shallow ocean water. Okay, but you can also see that it's not simple. Okay? Interspersed with these high-standing regions with the axial valley, there are these offsets that are at more or less right angles to it, 90-degree angles. You'll have one section spreading, shoot over another section of divergent boundary, shoot over another section, shoot over another section, and so on and so forth. You have these offsets. Okay? And these are actually transform boundaries. Those offsets themselves, we have one plate on this side going this way, the African plate. We have one plate on this side going this way, South American plate. Okay? So here they're pulling apart, but if we look right here, we have a plate going this way and a plate going this way, side by side, okay, across that particular part of the boundary because it's turned 90 degrees. And that's a transform boundary. So if we take a sort of cartoon picture of this, okay, this is maybe kind of what you would see in map view. So this is just a simplified version of what I just showed you with all the depths removed and just drawing in the plate boundary. So you have divergent parts where you're creating new oceanic crust, and you have these offsets that are at more or less right angles to it. And we could take a perspective view, so kind of, like we're flying in an airplane over the ocean floor, okay, and look at it this way. So we see the axial valley along the mid-ocean ridge spreading segment, the offset, and then another segment, okay? And the arrows here indicate the relative direction of plate motion. So across the spreading ridge, of course, they're going apart, but in this offset, they're actually going side by side past each other. And what we see in a bathymetry map is you have this offset, and there's kind of a crack in between, which is really obvious in some places, less obvious in others. Okay, but the crack actually continues past the spreading ridge on either side. But if you think about it in terms of how things are moving, okay, between the two ridge segments, we actually have side-by-side motion. But once you get past this ridge, both of these parts are on the same plate now. So in the case of the picture I just showed you, these would both be on the South American plate now. These would both be on the African plate. There shouldn't be any relative motion between them. So where would we expect on this simple map to find earthquakes? Okay, you would expect to find them on the red line, where you actually have side-by-side motion. Where else? On the ridges, right. You should certainly expect to find them here. You have spreading going on, and that's accompanied by earthquakes also. Okay, what about the third arrow? Should we expect to see lots of earthquakes here? There's a crack there, so there's something that could move. What do you need to have earthquakes? You need to have rocks sliding past each other. Would we expect these rocks to be sliding past each other? No, it's not a plate boundary anymore. So they're both on the same plate, and we assume that plates are more or less internally rigid. There's no internal motion. Okay, so we should expect, if we take that depth map that I showed you of the Atlantic Ocean between South America and Africa and plot the locations of earthquakes, just like we've seen before, it should outline the actual plate boundary, and we should only see earthquakes in the regions where there is relative motion across the plate boundary. And we shouldn't see earthquakes where it's no longer a plate boundary, even if there's a crack there that you can see in the depth. You're on the same plate on both sides. There should be no relative motion, so there shouldn't be very many earthquakes. Don't want to say none. Okay, never is a strong word, but you should see many fewer. All right, so back to our map. This is the same area. Okay, and then hopefully we can overlay some earthquakes on top of that, indicated by these little yellow dots. These are earthquakes. These are pretty big earthquakes. I think also bigger than magnitude 5 over the past 36 years. Just pulled off the web. And what you can see is the earthquakes pretty much outline the plate boundary. And in areas where you have a transform, right, the earthquakes are only happening in the transform. Follow the crack away from the ridge on this side, no earthquakes, at least no big ones. Okay, and you can look at all the other transforms here and pretty much make up the same story. Here's a big transform here, plenty of earthquakes along here, but once you get past that offset piece of ridge, no more earthquakes, even though there's still a crack there. No more earthquakes on this side, even though there's still a crack there. Okay, so there's a fundamental distinction to be made between the transform fault that's actually between two segments of ridge and a fracture, a crack, which is no longer seismically active, that extends to the other side of each ridge. Now, what we should see, even if there aren't earthquakes, if we go and sample both sides of this fracture zone, we should see, well, what? What might we expect to see if we had rocks from both sides of this boundary, or both sides of this crack? If we didn't have good bathymetric evidence that the crack was there. Let's say it was buried by sediments or something like that. Can you think of a way we might actually be able to detect it without looking at the depth, if the depth wasn't telling us what we needed to know? Some indirect way to infer the existence of a fracture zone? Yeah. You could look for a change in ages. Which side should be older? Why is this one older? Yeah, it's had to move farther away from where it was formed. So presumably it takes longer. It takes some period of time for this new piece of crust to get here, where it's juxtaposed against brand new crust formed on the other side. And so this one should be considerably older than this one. So we could look for age in the form of what are the oldest fossils that are lying right down on top of the oceanic crust, right? On the north side of that fracture, those should be older fossils than on the south side. We could look for offsets in the magnetic stripes. Okay, there should be an offset of the magnetic stripes, which indicates age. Or we could just pick up rocks and actually try to date them using their radioactivity, for instance. Okay, but we should be able to infer the presence of fracture zones, not just from their bathymetry, from the fact that there's a crack there, but also because there's an age difference across the fracture zone, even though both sides are on the same plate and there aren't earthquakes there anymore, at least not very many. Okay, so earthquakes occur on transform faults, in general not on fracture zones, which are the extensions of the transforms beyond their manifestation as a plate boundary. Okay, so no earthquakes on the fracture zone, just where you're between the ridge segments. Okay. Now, of course, oceans aren't the only place you get transform boundaries, and as residents of Southern California, they're not even really the most interesting place you find transform boundaries, because we turn out to live in a transform boundary, okay, which we officially mark with the San Andreas Fault. And a transform boundary, just like we saw in the case of the oceanic crust, it's a place where the plates are sliding past each other side by side horizontally. It's not that you're creating new crust. It's not that you're destroying old crust. They're just moving side by side past each other. And our local plate boundary between the Pacific and the North American plates is, in fact, a transform boundary at the San Andreas Fault. Okay, so this is a transform. It's seismically active. In fact, I think this is looking north, but I could be wrong. I think this is looking north. Okay, so that would make this North America. That would make this the Pacific. Does anybody remember which way the Pacific is moving relative to North America? Yeah, Pacific is moving towards the northwest. So this side's going this way. Relatively speaking, this side's going this way. Okay, should we expect to see transform boundary earthquakes along the San Andreas Fault? And we certainly see earthquakes along the San Andreas Fault, although not in Southern California lately. But it's going to happen, presumably, before too long. Okay. We'll come back to the tectonics of California in a minute, but there's one little sort of non-plate tectonics thing to talk about. It's actually relevant for understanding how plate tectonics works. And that's to point out that most earthquakes, most volcanism occur in association with plate boundaries, but not all earthquakes and not all volcanoes. And there are some that are actually worth talking about that don't. Okay? And a particularly important one, important type, is the hotspot, what we call a hotspot, an area of volcanism not necessarily associated with the plate boundary, although we also talk about hotspots on plate boundaries as places where you have especially voluminous magmatism, lots of extra volcanism beyond what you might expect just because it's a plate boundary. And in many cases, in particular the example of Hawaii that I'll show you, these seem to be long-lived features of the Earth. They aren't necessarily at plate boundaries, but there seems to be regions of the Earth where volcanism is happening over and over again, persistently for tens of millions of years, more than 50 million years in the case of Hawaii. And if we look at the amount of volcanism, particularly in the oceanic crust, something like 90% of the basaltic crust in the ocean you can explain as having formed at these mid-ocean ridges, divergent plate boundaries. But the other 10% or so doesn't really fit. Okay? And so these non-plate boundary or plate boundary in addition sources of volcanism contribute a minor but perhaps significant component to the total inventory of oceanic crust, and account for also a minor but perhaps significant amount of the total heat that's coming out of the Earth. Okay. And the interesting thing about these is because they're persistent, they stick in the same place, we think, more or less, they move a little bit perhaps, but more or less in the same place with respect to the Earth's deep mantle. Plates are moving. So if you have a hot spot that's fixed and the plates are moving over it, you're not going to just generate one volcano, but you're actually going to generate one volcano, then the plate's going to move, you're going to generate another volcano, the plate's going to move, you're going to generate another volcano, the plate's going to move, you're going to generate another volcano, and eventually you'll generate a long linear chain of volcanoes. And that can be used to back out, with some assumptions, which way the plate is actually moving relative to the deeper parts of the Earth. Okay? So these are interesting because they aren't really in and of themselves part of plate tectonics, but they give us information about how plate tectonics is working. Okay. So the classic and probably best example of a hot spot and a chain of islands resulting from that hot spot volcanism is Hawaii, which is, of course, a U.S. state. So we're here, Southern California, actually here. And if we fly southwest for a few hours, we get to Hawaii. Okay? And if you look at the bathymetry of the seafloor, there is not just a series of islands going from the big island of Hawaii out to Oahu and eventually to Kauai, but in fact a long chain of islands extending out past Midway Island, and then a chain of seamounts that extends essentially all the way across the Pacific Ocean up to Siberia. Okay, a long linear chain of islands and submerged volcanoes. Here's the basic idea of how that works. Okay, so we have the Pacific Plate, and the Hawaiian Islands sit basically in the middle of the Pacific Plate. Okay, and the idea is that we have essentially a fixed hotspot. There is some source of extra heat or extra melted rock that punches its way up through the oceanic lithosphere and crust, making volcanoes. Okay. But the Pacific Plate is not itself fixed. It moves. Okay, we have the East Pacific Rise down here. That's a spreading region. Okay, so we have new crust being created, going out generally towards the northwest. And eventually that material is being recycled, being subducted off the coast of Japan and Siberia and so on. Okay, so the Pacific Plate is actually in motion generally towards the northwest and is dragging itself over this hot spot. So what we should expect to happen over time is that any volcano that forms over the hot spot, by the time it gets very old, is going to have been dragged off to the northwest because it's stuck to the crust, and will eventually find itself no longer over the hot spot and will die because there's no longer a source of melted rock to it. Okay? So we have a hot spot, and what we should expect to see as we get farther and farther away is a chain of progressively older volcanoes, tracing out what parts of the Pacific Plate used to be over that hot spot going back into Earth history. We can look in this in a little more detail. So this is a little perspective map of the islands of Hawaii, the main islands of Hawaii. So the big island of Hawaii is right here. Mauna Loa, Mauna Kea, where the telescopes are. Kilauea, where the national park is, which is the most active of the volcanoes. There's actually a little volcano offshore. It's actually not little, it's pretty big, but it's still underwater, called Loihi. And this is where the vast majority of volcanism in Hawaii takes place, so we infer that this is where the hotspot is now. Okay? There's stuff coming up from deep in the earth here, lots of it in the case of Kilauea. It's been erupting more or less continuously for 26 years now. And then as we go towards the northwest, we get progressively generally smaller and in fact older islands as you go away. There's some not too old volcanic activity on some of them, but the majority of the volcanic activity seems to get older the farther you get away. So the big island of Hawaii, pretty much all the volcanic rocks you could pick up and get your hands on are less than 1 million years old, which is quite young. Remember, oceanic crust gets as old as 200 million. If you go out to Maui, something like 1.3 million years. Out to Oahu, 3 or 4 million years old. Get out to Kauai, something like 5 million years old. Okay? So from this, we can infer that this is where the hot spot is, okay, relative to the Pacific Plate, 5 million years ago, Kauai was over that same hot spot and has since been dragged to the northwest by a few hundred kilometers. It's a little harder to get your hands on rocks from submerged islands or islands that are covered up by coral reefs, but nonetheless, to the extent we can measure them, it looks like things get older the farther you get away from the present hotspot. And in fact, we can understand the shape of the big island itself, which has several volcanoes on it. It's not just one volcano, it has at least 5. In terms of the motion of the Pacific plate across this hotspot as a function of time over the past million years or so. Okay, and that's what this animation is going to show you if it works. This is from the Hawaii Scientific Drilling Project, I think by Daniel Stolper, but there are many co-authors, I'm sure. And the frame of reference here, just to keep you from being confused, is fixed relative to the Pacific plate. So what you should imagine when I'm showing you this little movie is that you're standing on the Pacific plate moving over the hot spot. Okay, so from your point of view, it looks like the hot spot is moving towards the southeast. Okay, and the graph shows 2 things. This is in red, the hot spot, which is just imagined in this case to be a hot spot that's 100 kilometers across. Okay, and wherever it is, you're going to tend to have volcanic activity coming up and building up a mountain over time. And this is a topographic cross-section, okay, showing the depth. So numbers above 0 indicate that there's an island. Numbers that are below 0 indicate that there's seafloor. By the way, you can see here, the seafloor coming into the starting point is bowing down. Does anybody have an idea why that's happening? Why is it getting deeper when you get close to the new island of Hawaii? Well, this stuff is, yeah, it's probably colder than where the hotspot is, so it's denser. But why would it be getting denser when you get close to the hotspot? It's not a subduction, though. This is in the middle of a plate. There's no plate boundary here. What is this thing? It's a big volcano, right? It's a big lump of basalt. It's pretty heavy. Right? And we have this idea of isostasy, that things kind of float on the asthenosphere. And it's on old crust. So the crust isn't all riddled with cracks. It's actually got some strength to it because it's been sitting there cooling down as a unit for a long time, 70, 80 million years. So you're essentially putting a big weight on the end of a beam, and it's just bowing it down. Okay? So this extra weight of the volcano is pushing down on the Pacific plate that's not right over the hot spot. Okay? And in turn, the Pacific plate is actually pushing up the volcano a little bit higher than it otherwise would be. Okay, so this is actually an example of an elastic response. The plate's actually being bowed down by the additional load of the volcano sitting on top of it. Okay, so let's run this guy and see what happens as a function of time. Okay, so remember, this is from the frame of reference of the Pacific plate watching the hotspot move towards the southeast. And as it moves, it's building up new volcanoes, okay, that are coming up above the ocean, and then the volcanoes are shutting down and starting to sink again because there's no longer being built up. They're moving away from the hotspot, things are cooling off, and they're sinking back down again. Show that one more time. Okay. So you can imagine over tens of millions of years, you're just building up volcanoes, they're moving off and then sinking. You're building up a new volcano, it's moving off the hotspot and then sinking. It's like a big factory. Okay, it's a factory generating volcanoes that then sink again. And this particular simulation was set up so that it ended up making something that looks like the modern island of Hawaii with 5 volcanoes at a maximum elevation of a few kilometers above sea level. Okay, are there any questions about that? Okay, so we've talked about how you can create new oceanic crust, new lithospheric plates, or these parts of a lithospheric plate at mid-ocean ridges, and how they get recycled at convergent boundaries at deep sea trenches. The implication being that ocean basins are enlarged or shrunk depending on what kinds of plate boundaries are inside of them or at their margins. And from that, we can infer that oceans actually have a life cycle of a sort. It's complicated, but broadly speaking, you can think of oceans growing when there's a mid-ocean ridge in them, okay, creating new material, and then shrinking if there's a convergent boundary inside of it or at the margin, recycling that older material. Okay? So you think of an ocean being born, growing, and then shrinking again, and ultimately perhaps suturing, dying when a continent comes back and collides with another continent, getting rid of the ocean basin altogether, such as the case of the Himalayas. And so in that life cycle, this would be an example of a birth. Okay, this is a picture from northern Tanzania in Africa, in the East African Rift Valley, which is an area where plates on either side are slowly starting to pull apart. It's not a very well-formed plate boundary yet. It's just getting going. Okay, but you have a continent that's slowly starting to pull itself apart, east from west. And looking at this, can you see any indications that this is in fact a plate boundary? What's something in here that looks like a plate boundary feature? Yeah, there's a big volcano here. This guy. A big active volcano called Odo Inyo Lingai, although I'm sure I'm pronouncing it wrong, but nonetheless. It's actually a really neat volcano. You can see kind of this white stuff in it. It's got very funny volcanic rocks coming out, very funny lava erupting that's actually full of carbonate instead of silicates like most rocks, and it's very low temperature. It's really funky stuff. There are some pretty cool movies you can find on YouTube and stuff about the lavas being erupted. They're actually so cold that they don't glow very much. They're just black stuff. It's like somebody spilled crude oil or ink across the surface of the mountain, and it's just running downhill, and it's really runny like water. It's funky stuff. Okay, any other indications that this is a plate boundary? It's a little tougher. It's not the cows. What do you see at a mid-ocean ridge? Right at the top. Exactly right. So at the top of mid-ocean ridges, there's usually an axial valley, right? Right at the top, there's pulling apart, and there's an area that's downdropped a little bit. What you can see here is that we're actually at the edge of an axial valley, and that's what the Rift Valley is. It's an axial valley. We see all these cliffs. Okay, and in fact, those cliffs correspond probably to faults that are downdropping the area here, where Lake Natron is, where the volcano is. And when you get away from the boundary, stuff is actually higher because you're on the margins of that spreading center. Okay, and this is baby. It's obviously not an ocean yet. Okay, there are cows there. There's not an ocean there. Cows and oceans usually don't mix. So we can think of that as being an ocean basin that's in the process of being born. It's not clear if it's actually going to ever become an ocean, but nonetheless, if it did, this is where it would start. We have a continent that's just starting to pull apart. Okay, we have volcanic material. We have earthquakes, indications that it is a plate boundary. And we have these sides coming down into a central valley. Okay? And if that continues to happen, we can imagine it pulls apart more and more. Eventually you start getting volcanism creating oceanic crust because the continental crust has moved off to the sides. And you actually get flooding by the ocean, and it becomes a sea. And we could call that a juvenile ocean. Okay? Typically not too wide, relatively narrow, more or less symmetric. Anybody give an example of such an ocean? Red Sea is a good example. The Gulf of California would be another example. Okay? Not very wide yet. We don't even call them oceans. We call them seas. More or less symmetric, narrow and skinny, but they are pulling apart. They're getting larger with time. Eventually, once the ocean gets wide enough, the continent develops a passive margin. The rivers are delivering sediment. It's just falling out, making up a big pile that gradually gets deeper and deeper until you get to the oceanic crust on the seafloor. And we could call that a mature ocean. Okay, it's an ocean now. What would be an example of a mature ocean? Well, how many oceans are there? There's basically only one wrong answer if you know the names of the oceans. The Atlantic is an excellent example of a mature ocean. Okay, Remember, we talked about passive margins as being Atlantic-style margins, like the east coast of the United States or like the European coast. And that would be because the Atlantic is a mature ocean. It's very broad, but mostly it has passive margins on the sides. And it's still getting bigger with time. Okay? Eventually, once this crust gets old enough and cold enough, it'll kind of want to be recycled. It becomes more dense, particularly the cold mantle underneath it, and recycles back into the hotter asthenosphere. You develop a convergent boundary. That convergent boundary may actually start recycling crust more quickly than it's created at mid-ocean ridges within the same basin, and the ocean starts to shrink. So at that point, it's not mature anymore. It's actually declining, or if it's about to disappear altogether, we could call it terminal. Okay, it's doomed. It's just not dead yet. Examples of this? Pacific might be a good example of a declining ocean, right? It's ringed more or less by convergent boundaries. And because the Atlantic is growing by sort of conservation of area, it appears that the Pacific must be getting smaller. So that would be an example of a declining ocean. Can anybody give an example of a terminal ocean? Might not call it an ocean anymore. Something where continents on either side are moving together and they're getting pretty close. May even be starting to touch each other. Mediterranean, excellent, yes. So the Mediterranean would be an example of a terminal ocean. In fact, Italy, which is geologically part of Africa, is already colliding into Europe and making the Alps. Okay, so it's actually colliding in some places. And then if you go south of Crete in Greece, there's actually a convergent margin south of Crete. Okay, and there are volcanoes, of course, in the Greek islands like Santorini that blew up 3,600 years ago. And so that would be an example of an ocean that has shrunk to the point where it's actually in the process of disappearing. Okay. Have any questions about that life cycle of oceans? That life cycle takes perhaps something like 200 to 500 million years. We had a supercontinent about 250 million years ago. It broke apart, right? And the Atlantic is still growing, so we can sort of get a lifespan just from that. The oldest oceanic crust we see in the ocean is about 200 million years old. That also gives us a sense of what the lifespan of an ocean is. All right. This, since I've already mentioned it in passing a couple of times and a couple of you asked, we don't just have nowadays proof of or evidence in favor of plate tectonics coming from inferences about how old the oceanic crust is and about earthquakes going down deep in the earth and where they form. We can actually see plate tectonics happening more or less in real time with GPS. And there are actually some other preceding methods that were used to measure the positions of places within the plates relative to each other with such accuracy that you can actually see them moving together or moving apart on human timescales, years, months. Okay, and what's being shown here is an assemblage of GPS data showing motions relative to a fixed spot, which is, I had it, and then I forgot where it was. I don't know actually where the fixed spot is here, but you can see that places on the Antarctic plate aren't moving very fast. So we can imagine fixed relative to Antarctica. Where are all the other plates moving? Well, you can see that pretty much everything in Australia is moving that way relative to Antarctica, okay, like that. So what kind of boundary is that? Divergent. So what kind of plate boundary what feature would you expect to find at that plate boundary? Mid-ocean ridge, and in fact, there's a very nice mid-ocean ridge right here between those two plates. Here we have North America kind of doing this a little bit, and we have the Pacific plate going like this. What kind of plate boundary might we expect to find there? Where it's mostly a side-to-side motion. Transform, right? And we have our San Andreas Fault. Here we have South America. It's a little bit confusing, but it's more or less fixed, maybe moving very slowly this way. Here we have the Nazca plate that's moving this way really fast. What kind of boundary would you expect to find there? Convergent. And what kind of features would you expect to find at that boundary? Mountains, deep sea trench, subduction zone volcanoes, right? You can make similar arguments about what's going on the other side of the Pacific as well. Okay? So we can actually see relative plate motions going on today. Okay. So going back to the idea of continental drift, there was this idea that 250 million years ago, the continents were assembled into one supercontinent that has since broken apart as the Atlantic Ocean, we found out when we learned about plate tectonics, began to form at a mid-ocean ridge, and the Pacific shrank as a result of recycling at convergent boundaries. Okay, and this is a reconstruction using magnetic lineations on the seafloor and other kinds of evidence of how the oceans have evolved as a function of time over the past 250 million years. This is going to cycle over again, I think. And what you can see is you start out with a supercontinent, and the Atlantic Ocean is born. The North Atlantic is born first, and then the South Atlantic starts moving apart, and the continents come into something like their modern configuration. So hopefully that looks a little familiar to you. The second time we see it, I want you to pay attention, if you can, to what India is doing. Here is India. It's actually wedged in between Africa and Antarctica. 200 million years ago, it stays stuck to them until quite recently in geological history. So they were part of the same continent. Still there. The North Atlantic is opening up. Still there. Now the South Atlantic starts to open up. India is still there. Oh, it's broken off a little bit. And then, right about now, zoom, off it goes on its own little journey right up into Asia. Okay? And then about 30 million years ago, kaboom, right? And we make the Tibetan Plateau. Yes? Madagascar used to be right in between them. So its relationship is very close to both India and Africa. It sort of came off, but didn't quite keep going. And so it's still close to Africa, but used to be right up against them, in fact, right between them. All right. So the last few minutes of lecture, let's focus in a little bit on California. We're not going to get finished with this today. We'll come back and do it at the beginning of the lecture on Monday before we start talking about about marine sediments. So here we have an elevation map of the state of California. Hopefully by now you know that we're down here. This is the Central Valley. San Francisco is right here. Monterey. Las Vegas is over here somewhere. Okay. And you look at this map and there's a lot going on. We have big mountains in the Sierras. We have a big low-lying valley in the Central Valley. Southern California has all these weird mountain ranges and low areas right next to each other. We talked about the borderlands offshore as being this strange, torn-up terrain. Turns out that many of these large-scale features we see in a map of California can be explained as the result of our local plate tectonic history, in particular over the past, let's say, 150 million years or so, fairly recent in geological terms. And in particular, the major features, the Sierra Nevada, this big range of mountains, the Central Valley, this big, roughly parallel, low-lying valley where a lot of the farming happens in our state, the San Andreas Fault, our local plate boundary that runs just to our north, the Coast Ranges, like Big Sur, and in fact the Salton Trough, the Imperial Valley, the Coachella Valley, Palm Springs, all can be understood if we just think about what plate tectonics has been doing in our local neighborhood over the past 150 million years or so. And what I'm going to show you is a series of movies focusing in progressively closer on Southern California. These are all coming from Tanya Atwater's work at the University of California, Santa Barbara. Tanya Atwater is a researcher who did as much as anybody probably to actually put California into a context of plate tectonics. She was a grad student in the late 60s, right around the time when plate tectonics started to be accepted, and she really took a close look at the geology of California and realized how important plate tectonics has been to shaping our state. Okay, so here's a movie showing the last 80 million years of history in the Pacific, as opposed to the Atlantic, like the previous movie. This is North America. So here's Florida, here's Mexico, here's South America. Southern California is right about there. And what we can see is, starting at about 80 million years ago, we have a convergent boundary, right? We have oceanic crust coming underneath North America. So what would we have expected to find there? It's a convergent boundary. So what are the features of a convergent boundary? So we have volcanoes, we have a deep sea trench, big earthquakes presumably. Okay. And then the interesting thing is, about 20 million years ago, that convergent boundary came into contact with a divergent boundary. A mid-ocean ridge actually came up against our local subduction zone. And at that point, it ceased to be a convergent boundary because now it was two different plates that were in contact with each other that were moving more or less side by side. So here we have the Farallon plate, in this case, coming into North America. Then in about 30 million years, this part of the divergent boundary hits the continent, and now North America is up against the Pacific plate, which is moving in a different direction. Okay, so the boundary actually changes. We go from a convergent boundary up until about 30 million years ago to a transform boundary at about 30 million years ago that grows as a function of time. Let's take an even closer look. Okay. So this is Western North America. This is where Southern California will be. We have a divergent boundary that contacts the margin of North America. So now we have a boundary between North America and the Pacific. And it's actually going like this instead of colliding with the side of the continent now. And so it's actually pulling out the continent and making a transform boundary where before there had been a convergent boundary. So California is an example of a place where we had a switch from one type of plate boundary to a different type of plate boundary, from convergent earlier in our history to transform more recently in our history. Okay, and that turns out to be really important for understanding why we have such a funky margin, why we have this weird up and down thing going on offshore, why we have these features like the Sierra Nevada, but also have features like the San Andreas Fault. And the last one I'll show is even closer in and more recent, just on Southern California. Okay, so SD here means San Diego, SB means Santa Barbara. And this is only over the past 12 million years or so. And what we're seeing here is Pacific plate going off to the northwest, North America staying fixed. And what's happening is actually kind of complicated. Instead of having just a simple single fault like the San Andreas, for the early part of this history, the Pacific is actually kind of dragging part of North America along with it, and it's spinning along like a ball bearing between two plates. Okay? And so we have this part of the western part of North America actually spinning out clockwise, dragged along that boundary and spinning around, trundling around. And it turns out that Los Angeles is basically what forms in the armpit. Okay? So Los Angeles is kind of what's left over after you swing the pre-existing crust out of the way. Los Angeles, remember we learned when I showed you the pictures of our margin, is kind of a hole that's been filled in with sediment. Okay, there's a giant pile of sediment under most of the LA basin, and that basin is there essentially because there was continental crust that got pulled away, sheared away, and spun out when we developed our transform boundary. All right, so we'll come back on Monday, and we'll look at what this plate tectonic history did to the shape of California.